Hello and good afternoon, everyone. Today we are in the sixth week of problem solving session. So in this course we are talk about that some organic molecule and we have to identify that organic molecule. Then when you draw the organic molecule, sometimes they give the same structure. Then how we can identify between these two structure which are same or not. So we have give that symmetry element. Then we talk about that chirality because chirality have the huge importance of the organic molecule. Some chiral molecule are non-resolvable like that. Mm, they can prefer that both the conformation are looking like same, but they are non-superimposable mirror image. That all the substituents all are same, but hello and good afternoon. So today's we are in the sixth week of the problem solving session. The course name was Symmetry, Stereochemistry and Application, and course instructor was Professor Angshuman Roy Choudhury. So I am Probin Maiti, teaching assistant of this course. So today's classes we are talking about some symmetric element, how we can identify them. Then we talk about that molecule is chiral or not, and today's we are talking about some cyclic molecule. So before start this, we are talking about like simple molecule. If a simple molecule should be symmetric if this molecule have that improper axis of rotation, and if this molecule don't have any improper axis of rotation, then this molecule will be disymmetric. And in these disymmetric molecules, if there will be no axis of rotation, then that molecule will be asymmetric, and that asymmetric molecules are generally the chiral molecule. So symmetric and asymmetric molecule are not chiral molecule, but if they are asymmetric molecule, then the molecule will be chiral. And a molecule is chiral means that from a two enantiomer, like one should be R and another will be S. And sometimes they are maybe give that two enantiomer differently, or sometimes maybe they are not given to enantiomer differently. So when I talk about that improper axis of rotation, so what is improper axis of rotation? Like this molecule, if you show that molecule, if after 90-degree rotation, so improper axis is after rotation and after reflection. If that molecule give that same molecule, then that molecule have that improper axis of symmetry. Like this example, if you rotate this molecule 90-degree, so what will happen? So these two hydrogen which replace each other. Then after rotation, if you reflect this molecule, so you get this one and this one are the same structure of this molecule. So this molecule have that S4 improper rotation. So if this molecule has S4, like this molecule have that symmetry molecule, so this molecule are not chiral. And what is the sigma plane? If a molecules, if we place a plane into the molecule such a way that the molecules can be half of each other, like one part is reflect to another part, then the molecule will be have the sigma plane. And that plane, if that plane will be contain the principal axis, then we call that sigma b. If they are not contain the principal axis, we call as sigma h. Like this molecule, if that molecule is will be like this, and your sigma plane will be cutting this molecule like this way, and your principal axis not contain that sigma plane, then that will be sigma h. So then, like some example how we can understand that molecule have symmetry or not. If a molecule have the C1 symmetry, like that molecule have only after 360-degree rotation, given that same molecule like this example, so that C1 symmetry and only E, if the point group is present in a molecule, then that molecule must be chiral, because after 360-degree rotation every molecule gave that same irrespective of anything. And if a molecule have only that sigma plane, like example of this molecule have only the sigma plane are present, but there will be no c axis, C2 or C3, then that point group will be CS. And if a molecule only Ci is present, so then that the only that point group will be Ci. So for this, only for these cases only E, that molecule will be chiral, and every cases that molecule are not chiral, so that molecule, so only that C1, if a molecule have only C1 or only E, that time the molecule is optically active, or this molecule is chiral molecule. Optically active means that molecule after optical rotations, so they can rotate the plane polarized light positive or negative direction, but this molecule don't have that behavior. Then we goes for the higher symmetry. If the molecule have the, you have found out that the molecule have the highest order of CN axis, and this CN axis, if that are perpendicular to that C2 axis, if a molecule have that more than number of C axis and your principal axis is perpendicular to that C2 axis, then this molecule, if they have that perpendicular to the C2 axis, then that point group comes D. If they are not perpendicular, then the point group coming as C or S. So if they have sigma H, and then the point group will be D and H. If they have sigma D, they have no sigma H, and they have both sigma H and sigma B, we cannot get, then that will be D and D. If there will be no sigma H, no sigma plane, then that point group will be Dn. N will be that how much C2 axis are present, how much C is present in that molecule. And if there will be only one C2 axis is present in the molecule and which are not perpendicular, if only one C2 axis, so they're not talking about that these are perpendicular to the another C2 axis or not. So that point group coming as C or S. If there will be sigma H plane present, then that will be C and H. The N is that number of symmetries present. And if there will be sigma B, then will be C and B. Like if there will be no sigma plane, maybe they are present as some improper rotation like S2 present or not. If that will be present, then comes as S2N. And if there will be no improper axis also present, only C, then that point group will be Cn. we have to find out that symmetry element of this molecule and comments among the optical activity. So if we talk about this dimethyl cyclobutane compound, and if we draw this compound like this way, so we have to talk about that molecule is symmetric or not, and that optical activity. So if you draw this molecule like this way, so our 2-methyl group and rest of its hydrogen. With this molecule we have find out that there will be some sigma plane passing to this. If you cut this molecule like this way, so there will be sigma plane is present. So if in a molecule sigma plane are present, so then that time that molecule are not be chiral. So that molecule optical activity is optically inactive. So the molecule have that sigma plane, so that molecule have optical inactive. Next is the similar case where that the 2-methyl are not in the same site, like earlier one is that 2-methyl is the same site, like as they are in the cis conformation, this they are in the trans conformation. So in this case also they don't have that sigma plane. Like now this is the cases where the 1-methyl is up, another methyl is down. Now there will be no sigma plane as case of cis one. So if there will be no sigma plane, so that molecule, and if this molecule are not giving the superimposed mirror image, so that the trans cases the molecule have that optical activity, so the molecule have optically active. And if you talk about the point group, optically active, but if you rotate like this your axis, and if you want to rotate this molecule 180 degree, then what will happen, this methyl which are down, so it will be come up. So this molecule have C2 symmetry. After 180-degree rotation, this molecule give the same molecule like this way. So this molecule have C2 symmetry, but that molecule also optically active, and also this molecule can present like two enantiomer, like as any chiral molecule given. If you compare that both the Cs between these two molecules, what the relation between these two molecules, so that relation between these two molecules, one is Cis, so that there will be no, they are not same molecule, so they are different, so they are relationship as diastereomer. Now the next cases, so if you want to replace that one is methyl and one is another group, then what will happen? So then cases, so there will be no sigma plane even in the cis or trans cases. So if you like this, so one is your methyl, one is your amine. So there will be no sigma plane and no C2 axis is present. So their molecule will be optically active. Both in this case also, if that molecule will be like this, where that both methyl and amine both is up. So that case also that molecule don't have any sigma plane. So both that cases the molecule is optically active and the point group is E, that is the C1. And if we talk about the relationship between these two molecules, so they are also diastereomer of each other. They are not homomer. This molecule have that mirror image, so that will be an enantiomer of that molecule. This example also we have seen, so both in that cis or trans cases, so that molecules have that the that molecule have the optically active um, and the relation between this and this they are diastereomer relation. Now in the case of 1,3 disubstituted cases, so in that cases, so we have that if they are in the cis conformation, so we have that sigma plane. So 1,3 disubstituted like this molecule we can draw like this. The 2 methyl is up. Then molecule have that sigma plane. So if they have sigma plane, so that molecule have optically inactive. Then next cases, soft, also that sigma planes also suggest that the molecular mesocompound. So next cases when that one is up and one is down, so then also we have that sigma plane. Like earlier 1 2 disubstrate, when they are in the trans conformation we don't have that sigma plane, but these cases, so 1 methyl is up, like this plane we have the sigma plane. So this molecule have their meso compound and they are optically inactive. So and the relation between these two cis and trans, they are diastereomer to each other. So this molecule have that C2, but this molecule don't have. Next, if we talk about that which have that different substituent in that 1 3 position, so in that cases you have that sigma plane like this way, so that molecule are optically inactive. And point group will be CS. Now if we talk about that tri-substitute one, then what will happen? If a molecule have tri-substitute, like there will be methyl down. In this case, this molecule are optically active because there will be no sigma plane. But this tri-substitute molecule will be like this. The 2-methyl is up. Irrespective of this methyl group is up or down. So both the cases, like these cases also, that molecule have that sigma plane. So they are optically inactive. Optical active. Even the next example for that cyclohexane molecule. So this molecule optically active or inactive. So this cis conformation, if we're talking about like this, so they have sigma plane when you are this planar conformation. So if this molecule have that sigma plane, we talk that if the molecule have that sigma plane, then the molecule is optically inactive. But this molecule have that optical activity. Because this molecule are not in this form, so they are prepared to in that chair conformations or board conformation. So if you draw this molecule like this way, sorry, so if you do like this way, and this your fluorine, which is up, fluorine, which is up. So one fluorine is that axial position and one is that equatorial position. So this is the equatorial carbon and this axial carbon. Now this molecule have don't have any sigma plane. So as they this molecule have don't have any sigma plane, so this molecule should be optically active. So this molecule are optically active. But so these conformations and these conformations are room temperature flipping of this carbon bond are happened. So at room temperature, if they are flipping each other so fast that so they cannot resolvable to each other at room temperature. So when we are cannot resolvable the two conformations, then that molecule is optically active, but that we cannot get that one enantiomer form as pure. So we are always getting that mixture of two enantiomer and which are continuously changing to each other. So when we talk about the planar conformation, that molecule looks like that molecule have sigma plane, that molecule are optically inactive, but this form can be changed easily and get that another form and which are not easily resolvable. So and if we talk about that relation between these two conformer, so both when the both fluorine is up and both fluorine is down, so both are the same conformations. So these are homomer to each other. They have optically active The real conformation is optically active, but at room temperature we cannot separate out the two conformer. So like this form I have written. So cis 1,2 dimethyl cyclohexane can exist the two possible chain conformations like this way. The axial and the equatorial position, this conformation equal energy and therefore present in the equal amount. And this is a pair of conformations. This cannot be resolved because of rapid interconformation of cis 1,2 dimethyl cyclohexane is an achiral compound. So we are not separate out the two conformers at room temperature. For that reason, the molecule are achiral. As though they are chiral, but we cannot separate out the two conformer. So for this reason, they are achiral. Then the conformer like this one, cis and trans, so they are chiral molecule, and the relation between these two are enantiomer of each other. Which is easily shown by the chair conformations where this fluorine we consider like the methyl. So if this one has one methyl is up and one methyl is down, so that at that mirror plane, we place the mirror plane where this methyl is up and this methyl is down is considered like this molecule and this considered like as this molecule. So they have that non interconvertible by rotation around the single bond, that is the ring flip. They are configurational enantiomer and can be resolvable. So they have the optically active molecule and they have the enantiomer of each other. So earlier, so 1,2 dimethyl cyclohexane when they have the cis conformation, so they are that chiral, they are achiral molecules because they don't have that any sigma plane when we are drawing in that uh, drawing in the chair conformations, but these two conformers are so rapidly interchanged to each other. So we cannot separate out. For as a whole, that molecule is behaved like a achiral molecule. Because when you talk about the chiral molecule, that the optical rotation should be positive or negative. So if the two conformations are present equal form, like one is so that after rotation, so if that rotation of plus is plus 50 and minus is minus 50, so overall that rotation one is minus 50 degree and one is plus 50 degree, but overall net rotation is 0. So overall net rotation is 0 is given all the molecule that those are not chiral. So overall the molecule is behave at achiral because these two conformers we cannot separate out. The next, you put the UPAC name of this compound. So UPAC name of this compound will be S 2 chloro 3 ethyl pent 3 and 2 all. So what we are learned today, so we are talking about that symmetry of molecule, and which molecule have that improper axis, and if that molecule have that any sigma plane, then that molecule are not chiral, so they are meso compound. But when that molecule have any of that CN rotation or asymmetric, then molecule are achiral. So like this example I have given. So when we are talking about that any cyclic compound, so for that cyclic compound, that sigma plane or any inversion of symmetry are present in that molecule are not chiral. So there are optically inactive molecule, but molecule have C2 symmetry, but they are given optically active. So these are not as a simple molecule like not a not cycling molecule like that. So they have the C2, but they are also optically active because they are non-superimposable mirror image they are given, and the conformation between this trans and cis conformation, they have diastereomer to each other. And also when there are two different substituent, so they are optically active molecule, and when they are the same substituent, so it is the trans cases, when the same substituent in the cis cases, they are optically inactive. And that relation between these two are diastereomer, and they both are optically active. The next one, these are optically inactive molecules because the sigma plane pass. Also, these the cases, and this molecule also sigma plane, but the conformation between this and this cis and trans conformation, so they are diastereomer to each other. And when we have that two substituents are same and both are in the 1,3 positions, so then the cases irrespective of that, so this molecule are optically inactive because that will be sigma plane passing to each other. But when there will be three substituents, then the cases between these three, so if this methyl one is both are up and one is down, at that alternative is up and that next position is down or up, with the cases sigma plane, so these have the optically inactive, but these cases they are optically active because this if I have it, so one is up and another one is down. Or and we talk about that cyclohexane molecules. So 1, 2 dimethyl cis dimethyl cyclohexanes, both both fluorine is up or both fluorine is down, so they have the same conformations, and these conformations are optically when you convert into the chair conformations, so they are optically active, but they are not resolvable. So they are the overall molecules are chiral because that chirality is coming when you rotate this molecule in a plane polarized light, that overall net rotation should be positive or negative. If the molecule are not one enantiomer is not excess, then the overall molecules behave as a achiral molecule. Next cases, when that trans conformation 1,2 dimethyl cyclohexane, so they are optically active, and these conformations are mirror image to each other, so they are enantiomer to each other. The nuclear name of this molecule. I hope all of you understand. If you have any question, you can ask me.